Great pleasure to welcome Helena Garcia Escudero. She's advanced graduate student at UC Irvine, and she'll talk about her field of study, which is early-ish universe. I think there are earlier universe people, but this is early-ish universe. And her advisor is keV-scale. Abazajan, if I've got that right. She's currently a Marie Sklodowski-Curie Fellow, which is a good thing. And she switched from atomic physics, right?
Yeah.
Switched to theoretical cosmology. And she's got 5 publications already, and she plans to graduate in spring of 2025. So anyway, thank you so much for coming, and we're looking forward to this talk.
Sure. Well, thank you so much for the great introduction. As you said correctly, I'm my 3rd year here at the University of California, Irvine. I did undergrad in Spain, and I also got a master in theoretical physics. I got a Marie Curie, and I went to do research on a different field, which in Germany, which was atomic physics, and I realized that didn't make me as happy as pursuing or answering questions on what was the universe, or how, why are we here, and what happened so many years ago when we can't see with our eyes what was going on there. So yeah, here I am, and I'm going to present today one of my most recent projects, and hopefully you can, after my talk, you can take away 2 main points that I want to make. I will start the talk by introducing and giving a little bit of background of who I am. And then I will motivate and give you some basic physics concepts, which are important to understand the work. Then I will continue explaining my calculations and finalize with the conclusions and the implication for the impact that this work can have in the very near future. So, well, first of all, I am a person that's interested in many things. I love physics, but I also want to say that I think life is fun in very different parts. So I love doing sports. As you see the top picture, I love horse riding. That's one of my main hobbies. But since I couldn't move my horses from Spain to the US, now I love running. That's the picture that you see on the bottom. I'm part of the UCI track and field team, and I enjoy doing sport with a bunch of UCI undergraduates, graduates. I have a lot of friends from sports. On the middle, you see me with one of my colleagues from my research group presenting a poster actually from this project when it was early on in the UCLA Dark Matter meeting last year. And in the bottom, on the middle and bottom of the slide, you see a research feature that the UCI Department of Astrophysics made about me. I love all of the aspects of my life, and I also enjoy traveling. The top right photo is with some friends enjoying some New York food. On the bottom, I'm with another friend making some crepes, and I also enjoy doing barbecues. The weather here in California is very nice. So, well, this is a little bit about myself, and now I'm going to dive into the physics. So hopefully I will explain a little bit better what's this sketch that you see on the right side of the slide. This was the first idea that I was writing on the board of my advisor's office. So from here we got into the publication that today I will explain. So first of all, let's dive into a little bit of particle physics. Don't be afraid, it's not going to be very technical. I'm sure most of you are familiar with the standard model of elementary particle physics. It's represented on the diagram that you see on the slide. So today we're going to focus on the particles that are on the bottom, which are neutrinos. So these are very interesting particles for many different reasons, but one of the most important things that I want to highlight today is that they are the only particles from the standard model that we don't know the masses. So I don't know if you can see well, but in all of the other particles, we have accurate value of their masses, so you see equal signs on the top of each of the boxes. But with respect of neutrinos, we only have upper bounds for the masses. So this is something that we need to do more physics to exactly determine what are the masses, and also we don't know what's the appropriate hierarchy of neutrinos. So these particles are very interesting because they're still very unknown. So it's worth exploring. But let me now say one thing that we do know about some neutrino properties that we have measured experimentally, which are the mass square differences that you can see at the top of the slide. So these properties are very unique because these observations are the only hidden sector model that has evidence for its existence from the lab. So these two mass square difference tell us that two sterile neutrinos, which are beyond the standard model particles of masses around 100 JeV, have to exist in order to produce these two known mass different scales. So this is a very, very important thing. So this brings up why sterile neutrinos are one of the unique beyond the standard model extensions that has proven existence from the lab, and this is a very strong claim. So if we assume that these two sterile neutrinos exist and commensurate with the family number of the standard model of particle physics, so let's consider that there's a third sterile neutrino that has complete freedom with respect of its mass and mixing angle. So in this talk, we're going to focus on KV sterile neutrinos, and I will motivate in the next few slides why. And I also want to say that KV sterile neutrinos are candidates for dark matter, which is one of the greatest questions that we have today in cosmology. What's dark matter? So just in a summary, neutrino oscillations give us experimental evidence that neutrinos have non-zero masses, although we don't know exactly what these masses are. So the neutrino mass generation proves the existence of sterile neutrinos, and we need two JeV sterile neutrinos to explain these solar and atmospheric oscillations that we have observed. So if we consider a third sterile neutrino, it has a complete freedom with respect of its mass and mixing angle, and its presence will affect experimental observations via new oxidation channels and patterns. And although it has not been detected yet, it's a detectable particle that maybe we can see in the future. So this was the little introduction or motivation on what are external neutrinos and why are they well motivated beyond the standard model extension. And now let's change gears, and I'm presenting another diagram that hopefully most of you are familiar with, which is the early or the thermal history of our universe. So first of all, let me tell you that this is just an invention or a drawing that has been, someone came up with it, or like there's many different types of like similar diagrams that you can find out. But this is just a model. Like this, we actually don't have enough evidence to explain yet what happened when the universe was like the first seconds of the universe. So it's just the first data that we have, or the first observations that we have from our universe, come from the Big Bang nucleosynthesis. So the amount of different elements that we observe from our universe. But before then, everything is just a model and an invention that it's very good, but we have to say that as scientists, we have to question if it's right or not, because we don't have evidence, and we are scientists, so we do need evidence. So after the predominant model of the early universe postulates that it underwent inflation, which diluted any prior constituents to cosmological irrelevance. It assured cosmological flatness, created the primordial density perturbations, and diluted any prior constituents to cosmological irrelevance. So when inflation comes to an end, its potential steepens, violating the slow roll and leading to the beginning of reheating. So this is one of the most important concepts for today's talk, which is the reheating temperature of the universe, which it refers to the temperature of the universe after this period of inflation, when particles transfer their energy into the standard model thermalized particles, establishing the initial hot and dense state. So this is one of the key parts of my talk, which is that usually the reheating temperature of the universe is assumed to be very, very high. With very, very high, I mean over keV-scale. But actually, this variable, it's actually a variable. So it's not, even if it's normally assumed to be a very high number. So as you see on the top of the slide, 10 to the 15 keV, the reheating temperature could be as low as 1.8 MeV, and could still be all of the observations and all of the theories and equations of the early universe that we have could still be fulfilled. So the earliest data that we have from our universe are these abundances of light elements from the Big Bang nucleosynthesis. So this sets this reheating temperature to be as low as 1.8 MeV. So Graciela Gelmini, which this is the paper that first, or one of the papers that first thought about what would happen if we actually consider a low reheating temperature universe. And actually, the answer is very surprising, because there's many like new physics or phenomenology that could arise when one considers a low reheating temperature universe. And this is what I'm going to present on one of the main parts of my work. So if we consider a lower reheating temperature, so around MeV scale, constraints on keV, in our case sterile neutrinos, are significantly relaxed, because in high reheating temperature universe there's a very long period of weak scattering, and this allows for the thermalization of sterile neutrinos, which oscillate with the actives and make this part of the parameter space, the mass and mixing angle parameter space, very constrained. But if we lower this temperature to be of order of MeV, these cosmological constraints are significantly reduced, as the scattering epoch is also decreased. So this implies that larger angles, so this means like the upper part of the plot. On the left, you can see the standard high reheating temperature universe, and on the right, you can see low reheating temperature universes. So with this low reheating temperature, we would much higher mixings are allowed by cosmological constraints. But that this is good, but now comes the part of the challenge that this why this work that I'm presenting happened. So I was working with the theoretical team of Hunter, which is an upcoming laboratory experiment that's going to explore this part of the parameter space, so KV range and high mixing angles. So low reheating temperature universe, as I said, are convenient because for explaining a potential signal that this experiment could detect, but they are not enough. So, for example, these blue lines that you are seeing on the plot represent the different phases of experiments. So Ki represents KATRIN, T represents TRISTAN, and H, the pinkish one with H represents Hunter. These are the different phases. So the initial phases are the upper ones. So and the ones that you can see on the lower part are future. With future, I mean like maybe 10 years on the future. So basically, the challenge that I was facing is I had to explain the possible signal that Hunter, this is this, I don't know if you see my pointer, but like the pinkish H1 line. So I had to come up with an idea to explain if Hunter could measure signal in their experiments. We need a model, a theoretical model that could explain, hey, Hunter has detected a signal of a KV sterile neutrino with a high mixing. So we had an idea, okay, we have to come up with a model that could happen in a low reheating temperature universe, since in this type of cosmologies, the cosmological constraints are significantly reduced, but they are not enough. So here I'm presenting an updated plot from all of the constraints that exist in a low reheating temperature universe. So the main idea is that the parameter space is less constrained than in a high reheating temperature universe, but as you can see, it's still very, very constrained. So all the existing constraints come, I'm not going to go into details of where all of these come from, but mainly they come from X-ray observations, so from Debra, NuSTAR, Hitomi, Chandra, so X-ray telescopes that place constraints on this parameter space. For example, Debra is the purple one that you see here. The Big Bang, the cosmic microwave background, the red triangle that you see on the upper right of the plot, also places some constraints. Supernova explosions also place constraints on this part of the parameter space. Galaxy formation, and all of these cosmological observations that we have constrain the parameter space, and we need to come up with a model that could explain the signal without coming into contradiction with all of these measurements that we do have. So again, you can also see the different phases or the different part of the parameter space that future laboratory experiments are going to explore. So some of them are Hunter, MAGNETO-𝜈, and TRISTAN, which is the new detector that's built in KATRIN that I mentioned before. So I already introduced you to Hunter. So it's the Hunter stands for heavy unseen neutrinos by total energy reconstruction. So it's an experimental tool it's being built in UCLA, and it will start hopefully taking measurements this year. So it uses the 131 Thesion isotope, and it's going to search for KV mass sterile neutrinos. Here in the plot, you can see what's the part of the parameter space that is going to dive into, and as the phases represent the different improvements in sensitivity of the experiment. But we have to first focus on the phase 1, which is the one that's coming up this year. So KATRIN is another of them. I'm just going to go briefly through them, since I'm not an experimentalist. I'm just while I'm working together with the experimentalists to to be able to explain the results that they should come up very, very soon. So KATRIN has actually already started taking measurements, and as I said, now they're building or they're implementing a new detector called TRISTAN that's hopefully going to improve the sensitivity, and it's going to dive into KV sterile neutrino. So KATRIN actually is focusing more on the AV range, but with TRISTAN, they're going to expand their measurements to KV sterile neutrinos. And MAGNETO-𝜈, it's probably taking their measurements by the end of this year. And the idea is similar, it just uses a different isotope, which is plutonium in this case. So, okay, here we are. We have experiments that are going to explore this parameter space. We have a low reheating temperature cosmology, but we still have a very, very constrained parameter space. So, what was happening? Yeah? Any questions?
No, but if you happen to have a microphone sensitivity button, you want to maybe turn it down just a little bit.
Okay, let me see if I can do that. Okay, so we were asking ourselves what was happening in cosmology if these experiments to see a signal. So a sterile neutrino beyond the standard model extension could be embedded in this richer phenomenology. So what you see on these plots is the standard, so the red diagonal line represents how radiation redshifts as the universe cools down. So on the x-axis, you can see the temperature of the universe. So on this would be an inverted axis, actually. So it goes from higher to lower temperatures. So it would be a time, a regular time x-axis, but inverted temperature x-axis. So reheating temperature is higher than the temperature of recombination. So this is the idea. We see how the energy density of radiation redshifts as the scale factor to the -4. And this would be the standard active neutrinos, which scale as, if we consider them in the standard model of particle physics, they are massless. So they redshift as radiation. And the blue line represents the energy density evolution of this sterile beyond the standard model extension. So these particles would be created at the reheating temperature, and they would redshift as radiation until the temperature of the universe drops below their mass, which they will redshift as matter. So this would be the standard sterile neutrino energy evolution. But what we thought with our model, if this is again still a very constrained parameter space, so we added a decay. So what would happen if these sterile neutrinos are particles that are not cosmologically long-lived? So if there's a point here where these particles will decay, it will involve another sterile neutrino or another dark sector particles. So we came up with, we realized that this decay could happen through two different paths. So the first one is it would involve the existence of scalar, which this sterile neutrino would decay until another KV sterile neutrino via this generic scalar. So this is one of the mechanisms, and the second one, it would be just including the sterile neutrino would decay just into another 3 sterile neutrinos via a C prime boson. These are on the right hand of the plot. You can see what are the 2 Lagrangians associated to these 2 different cases. And in both scenarios, we would introduce a new mechanism of sterile neutrino decay within a dark sector. So from the sketch that I showed you on the previous slides, this is actually the real calculation that I derive with a reheating temperature of 5 MeV. So the blue line that you see on the plot is the same plot as before. So on the y-axis you see the energy density evolution, sterile neutrinos. On the x-axis you see the temperature of the universe. So the vertical line that you see here represents the reheating temperature, and how the energy density of these sterile neutrinos would scale as the scale factor to the -4 until a certain time in which this until a certain time when the temperature drops below its mass, they will decay as matter, but at a certain point they would decay via either two of the ways that I presented. So how did we calculate this plot? So we calculated what fraction of these new particles would add up to the number of extra relativistic species, which we can measure from cosmic microwave background observations. So we have to keep that constraint into account. So we balance how much production of these sterile neutrinos we had, how much time they were living during the early time of our universe, and when they decayed. So following this calculation, we present that our model has a wide range, so the decay can happen at several range of times during the early history of our universe, all of them fulfilling all of the constraints coming from the measurements of the cosmic microwave background of the number of extra relativistic species. So different initial sterile neutrino production densities, that's what you can see on the different color lines, could match the same density relative to the active neutrinos. So this is one of the observations that we had to fulfill and we had to take into account in order to keep all of the cosmological constraint into account. So more production, this is the red line, would involve an earlier decay, and a smaller production could allow these new particles to have a longer life until their decay. And this is the decay could happen. The red line represents the earliest decay, which would be the decay would happen when the temperature of the universe is that of the mass of the sterile neutrino. In this plot, in particular, is 100 keV sterile neutrinos. And the green line represents the later decay. This would happen at the time of when the radiation and matter equality. So when the temperature of the universe is that of the radiation matter equality, this sterile neutrino would decay. And all of the scenarios within these two limiting cases could be allowed. So this is our final plots with a low reheating temperature universe and dark decay. So we represent different low reheating temperatures, and the first one is the one associated to the limits, which I said at the beginning of the presentation, that's said to be 1.8 MeV. So what you see here is the updated parameter space. So what parts of the parameter space are allowed? So all of the ones that you see on the white. So below this vertical line, all of the things that are below are not allowed by the model. Like this involves a number of n effective, which is the number of relativistic species in the early universe. That's below what Planck measures. So this is not, this is observationally, it would be constrained. So the signal below these lines could not be explained by our model, but the range that you see above, like the white part, would be. The only cosmological constraint that remains are those from beta decay experiments. So this black contour and a yellow contour, and we also still have some CMB constraints that you can see on the hash red lines. But all of the other, the white part is allowed. And probably in this case, you don't see it, but there are two lines. One, I see, well, let's see. So there are two lines. One is associated to the N effective measured by Planck, but there's another N effective that's a little bit higher. That's the one that you can infer from measurements from the earlier universe, so supernova explosions. So I don't know if you're familiar, but there's another cosmological tension that is called the Hubble tension, which claims that the expansion rate of the universe today is much higher than the one that's inferred from the cosmic microwave background and Planck observations. So using that measurements, the value of N effective is much higher. So with this model, we could reproduce also the N effective that it's derived from those measurements. So this is a very nice idea, since it can prove it can explain the observation from these upcoming laboratory experiments, but it's also in accordance with measurements from the N effective of the early universe. So it can also alleviate this Hubble tension that it is in our cosmologists' minds for such a long time, and it's kind of a headache because we really need to know what's happening with the measurements from the supernova and the standard model of particle physics, why they don't match each other. So this model has this twofold objective or twofold consequence, that it explains these upcoming laboratory experiments signals, and it also could explain or alleviate this Hubble tension. So this is the other of the plots that we calculate. So this is also a low reheating temperature, but a little bit higher. So this is the case of 7 MeV. And what you see in the plot, it's again the contours below the diagonal lines are not permitted or are constrained by the measurements of N effective, and the ones above these diagonal lines could be detected. We still have the constraints, in this case just the beta decay constraints. We don't have CMB constraint in the case of 7 MeV. So the 7 MeV reheating temperature would be a more ideal scenario for these experiments. We could the signal of Hunter could be if Hunter or MAGNETO-𝜈 or TRISTAN detect signal on these parts of the parameter space, our model would explain it. And in addition to it, if the signal is above this lighter blue line, it could also be in accordance with the N effective value derived from the Hubble tension. So again, the main conclusion is that this model can happen without violating any cosmological constraint, and can provide an extra number of relativistic species that would alleviate the Hubble tension. The little plots that I have on the slide is from another of my projects, where we tested how different beyond the standard model extension did on solving the Hubble and some other cosmological tensions, such as the SA tension. And you can see how a higher number of relativistic species, that the purple Gaussian that you see peaks at higher values of the expansion rate of the universe, that's H0, with respect of what's predicted with the standard cosmological model, that's represented with the green Gaussian line that you see on the plot. So this brings me to the conclusions of my work. So, and the main ideas that I want you to take away. that low reheating temperature cosmologies open up untested possibilities that are worth exploring, and the reheating temperature of the universe is actually a parameter. So normally it's set out to be very high, but it actually can be low or lower. And that's something that maybe you can apply to your research, or maybe that's something that could change the standard conventions that we have. Current laboratory experiments may detect within a few years the first detected remnant from the untested pre-BBN era, which can be a keV-scale neutrino. So this is very exciting that in the next few years we can detect again, we can have the first data from the earliest time of our universe. And its presence can actually explain the Hubble tension. That's a today problem that we are facing. And all of these would be an important funding for cosmology, particle physics, and astrophysics. And also the usual assumptions of the early universe will be significantly altered with a low reheating temperature cosmology. So yeah, low reheating temperature cosmologies are worth exploring. Thank you so much for your attention, and let me know if you have any questions.
Thank you. That was a lot. That's a very interesting hypothesis you're exploring. What assumptions of the early universe would be altered?
Basically, like the main one would be the reheating temperature of the universe. So as I said, like in standard cosmology, it's assumed to be very high. But for example, I have that's one of the questions that I have when I give this talk. Baryogenesis. So the standard baryogenesis mechanism has to be changed from what's normally assumed in the scenario where a low reheating temperature happens. And the standard baryogenesis mechanism assumes high reheating temperature universe, but there are some other baryogenesis mechanisms, which one of them, for example, is Affleck-Dine baryogenesis, that can happen in this low reheating temperature scenario. So that's for an example of what assumptions should be changed. So standard baryogenesis can happen in a low reheating temperature universe. And with standard is what I don't like using the word standard, because we don't have any data from our universe during baryogenesis. So all of the things are models, and the standard one is just the one that is most commonly used, but we don't have any evidence that's the right one. So we just need to like Affleck-Dine baryogenesis, substitute this standard baryogenesis that's normally assumed.
Great. Yeah, you took my second question, which was, would the matter-antimatter asymmetry be changed? And that's an emphatic yes on that.
Yeah.
Yeah, if you go back to your plot where you had the reheating temperature set to 5 mega electron volts, I think it was back a couple slides, where you had the different density. Yeah, that one. Okay. If the density happens to be anything but the green curve, would that rule out the sterile neutron, or sorry, the sterile neutrino as a dark matter candidate?
Actually, that's a very good question. So KV sterile neutrinos are candidates for dark matter, but in this model, we are assuming that they are not the dark matter.
Okay.
Because of the fact that they decay, right? Like,
right.
So KV, those are different points, and I'm happy that you made that question, because I forgot to mention. So in this model, we're not assuming that they are the dark matter.
Thank you.
Mm-hmm. Mm-hmm. Yeah.
This is not my expertise, so please stop me if this doesn't make so much sense, but. If you're trying to probe this to find if you're in this regime,
Yes.
that means that, does that mean that something about how we understand inflation would need to change in order for this regime to take over from after inflation? Does that make sense?
No, I mean it does. I'm not an expert on inflation in particular. Inflation, I don't think it shouldn't be affected. Is more, for example, baryogenesis would, but I don't see how inflation would be affected by this, like a lower reheating temperature. I don't want to say anything right. Wrong. But inflation shouldn't change within these scenarios. There are some things like baryogenesis that would. But I don't think that inflation would be affected. And actually, another of the projects or the ideas that I have in mind, I said that this reheating temperature can be as low as 1.8 MeV. So I'm planning to recalculate this more precisely using it hasn't been very studied, and there are some little details that I want to make sure on the calculation that has been done right. So that's one of my future projects, precisely understand and calculate how to set this low reheating temperature minimum lower bound, and check that all of the cosmology up to that point is good. But what we know from now, it is yeah. Michael.
Isn't the reheating temperature set by the inflationary mechanism? So it would be sort of a response.
And actually you're right, it is. So I wouldn't know from the top of my head with inflation mechanism. It's the one that should be associated to this lower reheating temperature. But sorry for that. But they're as the same as the afflecting baryogenesis. Maybe I can. I'm not an expert on that part, on how exactly to modify inflation, but there is there has been research on those done along those lines. So this you can modify the and that's what I meant by the cosmological assumptions should be modified. They can be modified without unfulfilling all of the cosmological constraints. There just need to be some modifications. So yeah, sorry.
As far as I understand, I mean, I haven't looked at this for a while, but yeah, the inflationary mechanism is pretty ad hoc. I mean, you just put in some sort of potential and you say, okay, I'm going to choose this so that I get a particular reheating temperature, and then see if it's consistent.
Okay,
so,
thanks.
So I think, yeah, but it's been a while.
Yeah, I think you're right, and thank you for that. Yeah, it's just choosing the appropriate model, and this would work. Yeah.
Thank you, Michael, for asking that question much better than I could.
Thank you so much.
Yeah, anything else? Burning questions? There's one. There's Michael again.
Are there any particle physics motivations that you know for this sterile neutrino?
Can you repeat your question?
Are there any motivations from particle physics itself for the sterile neutrino, or is it more something that could help explain things like the Hubble tension and stuff like that? So it's useful, but
I don't exactly understand what the main that. And I kind of understand what you say, but I'm not sure. The main idea is that the sterile neutrinos explain this, but I don't know if that's what you mean by the particle theory. So to explain this observed mass square difference from atmospheric and solar neutrino oscillations that we have measured, sterile neutrinos can explain them, and this is something that we have evidence for, right? So-
Okay, so this is something like the other component of a seesaw mechanism or something
Exactly.
like that. Yeah, okay,
Exactly.
fine. Great.
So yeah. So that's kind of the evidence, like, or the motivation. We still can't have any other, but maybe.
Mhm. Yeah, so I'm gonna see. Good, well, I'm glad there are mysteries left to solve in the universe, because that gives us all job security. Thank you so much for joining us today, Helena. It's a super pleasure to get to meet you and talk to you some more. And this is really interesting stuff, very thought-provoking, and I hope that wouldn't it be exciting if one of those experiments actually discovers a neutrino down there?
Obviously, yeah. I'm thrilled. I like what I do, and doing research is very exciting. So yeah, thank you everyone for the very good questions too. I really appreciate. And I left my email, so if anyone has any like follow-up questions, I'm more than happy to answer them.
Very good. All right, let's thank our speaker one more time.